So that poster presentation, you'd basically be printing out on approximately 6 to 10 sheets of paper a description of the data that you have, descriptive statistics, means, medians, frequencies, maybe a couple of charts, maybe describing the population, the data that you collected, and so on and so forth. Besides the descriptions, then you might talk about, or you actually might, before that even, you might introduce it to describe what you're trying to demonstrate, what you're trying to prove. Perhaps it's an analysis of how insurance affects whether a person gets an influenza vaccine or whether there's other factors that might influence that. That's one of the data sets, I believe. So you could print this out. Now, when I say 6 to 10 pieces of paper, you're going to print on these pieces of paper. The text and the charts are going to be large enough for you to be able to read from a few feet away. So we're not really talking about filling up single-sided, single-spaced text on that amount of paper. So when you look at the pictures that are associated with this, you'll get a better idea for this. So you'll see the rubrics for what should be on there, and that includes what kind of statistical tests you're going to apply, what the results of your tests are applying, what your conclusions are. And if you do this, I'd like you to submit them as a PDF file or as a Word document or something like that, and print them out and bring them to class, presumably on either Tuesday or Wednesday, either one of those 2 days. Bring them to class on either one of those 2 days and present your findings. Give us a 5 or 6 minute presentation on what you've done. So you could do that in lieu of taking the exam. Okay, the exam's not going to be that challenging. You're going to get a couple of shots at it, but it would also be very nice if some of you guys decided that you might want to do this presentation, because it'll demonstrate it'll be not only good for you guys that do it, but also for the people that you're presenting to, because they'll see an actual application of what we've been learning for this semester. Now, one caveat: if you're going to do that, I would like to know by Thursday of this week. Give me an idea of what you're planning on doing, where your topic's going to be. Show me what data you expect to use, and maybe a little bit of your descriptive statistics and what test you plan on applying. That way you're not going to be blindsided and wind up doing something that's not appropriate, or apply a test that will not work for what you're trying to do. Okay, so if you're interested in doing it, let me know by end of day on Thursday so I can give you feedback so you can work on it over the weekend if you need to. Okay, so and I'll also be posting somewhere where you can tell me which of the 2 days that you would like to present if you're going to do that. Okay, so at any rate, that's the way I'd like to handle the exam and the project. Again, it's your choice. If you'd like to give me some feedback on that, I'll put a discussion thread on Blackboard. So after this evening, I can go over there and answer your questions further, and give you some more information if you need it. Okay, so that's where we stand there. On the exam, I thought you guys did pretty well. I'm thinking like tomorrow night, maybe I'll go online for about a half hour or so. And if you guys have questions on specific problems on the exam too, I'll answer those. I'll answer those. I'll work through them with you. I know, for instance, what was it, number 10, where is it like 6% or something like that? The one where you had to describe what the percentage of the population was between 180 and 186. A lot of people had issues with that. I think there was another problem that also kind of tricked a lot of people as well. But what's that? Needs grading in terms of, is there a grade at all? Oh, by the way, there's someone taking a makeup exam tonight. So if you were able to access your grade and take a look at which questions you got wrong before, temporarily until tomorrow, you won't be able to access that until they finish taking that makeup. Okay, so, oh yeah. I guess that's Christine. I think that answers your question, right? Okay, good. All right. So unfortunately, I had to take it offline for a time. As soon as she gets done with it, or this evening or tomorrow morning when I get around to it, I'll do that. So I'm going to introduce this topic kind of a little bit freewheeling right now, and at the, at about 7:50, about 6:15, 6:30, I'm going to ask you guys to take a look at the lecture, Levi's lecture. Now, the lecture is an hour and 15 minutes long. I think you can probably start about 10 minutes in, actually, and you can scrub through it a little bit so you don't have to spend the whole, right now, don't spend the whole hour. So I'd like to try and get you guys back here by about 7:15, 7:30, so that like we can then do some application of some of the stuff that we're learning, this new function that we're talking about called chi-square, odds ratio, and relative risk. Okay, so I'm going to start. FoxPro is another browser. You can download it if you just Google, just go to naturally Google will try and encourage you to use Chrome. But if you Google FoxPro, one word, FoxPro, it'll take you to a location where you can download it and install it. It's a pretty good browser, and it's pretty popular. It's free, of course, like all the other browsers. Once you install it, you should be able to do that every once in a while. It'll ask you to update it. It's a pretty secure browser. It's got a lot of plugins if you're into that stuff as well. But you might want to install FoxPro on your system so you can do the exam. Like I said, though, I'll give you the option of I'll also provide a Word document where you can enter your answers. So if worst case, if we do have a freezing problem again, you'll be able to deal with that. But I'm told that according to ICET, they feel the problem is with the interaction with Blackboard with certain browsers like Explorer and Chrome and Safari. But I'm sorry, not Fox, so Firefox. Did I say FoxPro? FoxPro is an ancient database that an ancient database program that was marketed by Microsoft for a long time. But yeah, I meant Firefox. Okay, okay, good. Yeah, Firefox. Fox Pro. Okay, so at any rate, probably hadn't said that word in about 20 years. So at any rate, uh, you should have no problem finding it and downloading it and installing it. But that should solve our problems on that score. So just for you guys that are online now, how do you guys feel about dealing with the exam that way? Anybody have any concerns? Or you actually tell you the truth, if you want, you can email me if you want to talk about it privately, or I'll also put a thread up on Blackboard where you can discuss it as well. Yeah, I'll get it up Sunday night. So if you want, you can get it done over those anytime over those 3 days. The only thing is like our exam here, each time you take it, you'll have a 3 hour window to take it. So once you start, you got to do the whole thing, right? And then you'll have a shot to take. You'll have you'll be able to take a mulligan, right? Anybody use that? That's still a popular term, right? Mulligan, like a mulligan is like a do-over, right? So you can take a mulligan on it if you don't do very well at the first shot. It won't give you the answers, but it will tell you which ones you got wrong. So you get a second shot at it as well. Okay, but I've been pretty pleased with the way you guys have like kept up with the work and done the homeworks and so on. And that's another thing, by the way. If you have any assignments where you don't have 100%, there's no reason for you not to go back and redo those homeworks and increase your grade on those homeworks, right? Because the point of the homeworks is for you to learn the material. It's not a test per se. The homeworks you're allowed to collaborate with other students on it, work together on it, and so on and so forth. So there's no reason for you not to be able to go back and maybe take another look at it and figure out where you might have gone wrong. So take advantage of that as well. And also, those of you that haven't done it, this is a great weekend to do the city program certification, which I told you to do the first week when things were not as hectic. But nobody likes to hear I told you so. But I did tell you so. So at any rate, it would be a good time to do that as well. Okay, so let's move on to what we're going to talk about tonight, and that's this idea, this idea that up to now we've been working with numerical variables. Right. So for instance, let me see if I can get this working. Come on. Oh, that's working there. Oh, it's not looking so good there. Look at another one of these pens. Hang on a second, just working on something. Oh, something happened here. On the side. Boy, technology is failing me left and right lately. Oh, here we go. I think it's working now. Yep, here we go. Yeah, it came on, right? I think my cable is damaged there. I think that's what's happening there. Okay. All right, here we go. So, we've been working almost exclusively with numerical data so far. We've been finding the mean, the standard deviation. We've been working with samples and finding a standard error. We've been finding confidence interval. Confidence intervals are intervals that we use to determine the range within which we have a certain amount of confidence that the true mean, again, something that we're referring to a numerical variable, what SPSS calls a scalar variable as well. So far, that's exclusively been the territory that we've been working in. Okay, so now we have like kind of branched out a little bit, right? Our main place where we branched out was when we were talking about the binomial distribution, right? And you remember that. And that's when we had a function that had two values, either a yes or a no, success or failure. For instance, somebody had diabetes, or out of the population that didn't have diabetes. For instance, if you had 10 people out of 100 that had diabetes, the proportion or the rate or the prevalence of diabetes in that population, at least in that sample, is equal to 10%, right? Or the probability of picking a person out from that population, a randomly selected person, for instance, that has diabetes would be 0.10. So we looked at the only place that we really looked previously at a categorical variable, because this is a categorical variable, isn't it? The name of the variable is diabetes, and the values that it might have are yes and no, right? That's categorical, right? So really, thus far, the only variables that we've dealt with that were not numerical were these binomial variables. Well, in fact, we did kind of play around with these a little bit. One of the things that we said is, the mean x bar and mu. Well, that's just enough. That's what we call a point value, something that tells us the middle of that distribution, right? The mean, the middle of the sample, and mu, the middle of the population. Hopefully, x bar is a pretty good estimate of mu, but isn't always, right? Well, we have a point estimate for proportions for categorical variables that are binomial as well. Okay, if we when we're dealing with a sample like this one we just had, 10 people out of 100, we call that p cap, right? That's the proportion of our sample of the people that have diabetes. Of course, that represents an estimate for the true population proportion, p. And we know that we handled this the same way, a very similar way that we handled the idea of dealing with numerical variables. We said, anytime we take a sample, we're going to know what the proportion of that sample is. And if we sample it carefully, it's random, it's independent. If the distribution is normal, the distribution of population is normal, then we may know the proportion of that sample, but we're never going to know what the proportion of the population is going to be for sure, right? P is always going to be a question mark to us. But just like the mean, we could calculate a confidence interval. for this proportion. Okay, if you guys remember, the way we calculated a confidence interval would be to take p cap and add and subtract some margin of error from it, just like we did with the mean. Okay, in this case, it's going to be equal to, well, I was going to say t, but we really don't use t here. We use z, right? Z for, say, alpha is equal to 0.05. We use z, and we use z because one of the rules we're going to follow when we're dealing with binomials or with proportion is that the sample size is always going to be large. And that's typically true of most studies where you're dealing with binomial outcomes, right? Usually dealing with sample size 100 people, 1,000 people. You could even be dealing with a sample of 10,000 people, for instance, right? It's always going to be large. And we're going to have a second rule that we're going to add to that. And that is, is that neither side of this proportion can have a sample size n, I'm going to make you small n here, that's less than 15. Okay, so in other words, this wouldn't be a big enough sample for us to calculate a confidence interval because even though it's a sample of 100 people, only 10 of them have diabetes. So maybe, now if I was going to take the same proportion, if I took a sample of 200 people from that same population, we might have 20 people that have diabetes, still 10% prevalence, right? So that wouldn't be an unusual outcome. But this one is satisfactory because the sample size on both sides, at 20 and 180, sample size on both outcomes, successes and failures, is going to be over 15. Okay, so I can say z times my standard error. Okay, now my standard error here has a special calculation. Our standard error is equal to the square root of p. Actually, it's going to be p cap. It's p, but for all practical purposes, that's really p cap because we never know what p is, times 1 minus p over the sample size, right? So we're going to use that as p cap. So if I'm looking at this sample, 20 diabetics out of 200 people that we sample, then our standard error is going to be equal to the square root of 0.1 times 0.9 divided by 200. Okay, so it's going to be equal to, let's see, 0.1 times 0.9 is 0.09 over 200. Okay, and I'm going to calculate that. Okay, 0.09 divided by 200 is equal to 0.00045. Well, now I have to take the square root of that, right? I've calculated what this is, but I got to take the square root of it. And I take the square root of it, and it's 0.021. I'm going to round it off to 0.02 for my purposes tonight. Okay, you wouldn't round it off that severely, but I'm going to do that for our purposes. So this is equal to 0.02. That's our standard error. So for this particular sample, our 95% confidence interval is going to be 0.10, right? The 20 over 200 p cap is 0.10, plus or minus 1.96 times standard error, which is 2. And again, I'm 0.02. Okay, so again, I'm going to say 2 times 0.02 is 0.04, so it's 0.10 plus or minus 0.04. Again, a gross oversimplification, but save a little time. So our 95% confidence interval is 0.06 to 0.14. Just like we were dealing with the mean, we can say that we are 95% certain that the true value of the population prevalence of diabetes is between 6% and 14%, right? And if we had a bigger sample, it would be more precise, right? Because what's going to happen when we have, again, this is kind of a little bit of interpretation that we got on the test every once in a while, which most of you guys did pretty well on, okay? If the sample size gets larger, the denominator gets larger, then this fraction gets larger, then the square root gets larger, right? If this gets larger, this fraction gets smaller, right? The bigger the denominator is, like 1 over 200, if 1 over 400 would be a smaller number. As the denominator gets larger, this fraction gets smaller, our square root gets smaller, Since our square root is part of our margin of error gets smaller, so this range gets narrower. As the sample size gets bigger, the confidence interval gets narrower for the same level of confidence. Okay, so that works out pretty well. Now on the test, if I double this, I'm taking the square root, so it doesn't half the standard error, right? In order to half the standard error, I need to quadruple this, right, times 4. So then when I take the square root, it's double the standard error, right? That's why we need to quadruple that number instead of just double it. Okay. Isn't the sample? No, the sample. The outcome is we sampled 200 people, right? And 20 of them had diabetes, and 180 of them did not have diabetes. So the population prevalence, the sample prevalence was 20 out of 200 people. It's interesting that you brought that up because we're going to be contrasting something called relative risk and odds ratio shortly, and it's exactly this kind of thing that this kind of way of interpreting what this percentage is or what these odds or risks are that's going to impact the difference between odds ratio and relative risk. But we're going to see that in a second. Well, I decided that I couldn't use that. Remember, I couldn't use that because my sample size was too small. The 100 wasn't too small, right? The total number of people sampled, but the 10 was less than 15. So in this one, there were 10 people that were diabetic, 90 people that were not diabetic. So this side was sufficiently large, but this side wasn't sufficiently large, right? So I couldn't use this to calculate my confidence interval. So I just went back to that population. I took another sample, and this time I got 20 out of 200. Yeah, you get the idea, I think, now. Right. Yes.
So you got the 0.1 from 20 divided by 200?
I got the point. Yes, 20 divided by 200 is 0.1. Yep. Okay. So, all right. So now let's take this to the next step. Okay. It is possible that you might wind up in a situation where I say, okay, let's compare the population of seniors who are receiving Medicare, right, versus population of seniors who are not receiving Medicare, right? Let's compare the two of them in terms of like how many of them have been diagnosed with diabetes. Okay, now let's say I take a sample of 200 from each one of these two groups. And this group, it turns out 30 out of 200, right? That's in other words, that's 30 people are diabetic and 170 people are not diabetic. Okay, and this population, 20 out of 200 are a proportion, our prevalence are diabetic. So P cap for this population is 0.15. P cap for this population is 0.10. So now, if I want to compare these two, I'm not really interested in the outcome of these samples. I'm really interested in what's the proportion in this population, just like when we do our t-test for when we have a numerical variable. So I want to compare these two, right? Well, we can compare these two exactly the same way that we compared our numerical variable. I can say, well, I want to see how far apart these are in terms of standard errors. How many standard errors apart are these two? Well, let's see. That's going to give me a t-score if I were using a numerical variable, right? Well, in fact, since our sample size is large, always when we're dealing with binomial variables, I'm going to call z. Instead of using t, I'm going to use z as our z-score for our probability of being wrong if we reject a null hypothesis. I'm going to base that on the z distribution rather than the t distribution because we're always dealing with a large sample. Okay, well, what do I need to know there? I have to compare P cap for Medicare recipients versus minus and compare it to P cap for non-Medicare recipients, right? There's a difference between those two proportions. for those samples. And I'm going to put those over the standard error. Okay, well, we had a little bit of a problem there before when we calculated standard error for when we did the t-score, and that problem was now that we have two proportions, whose standard error do I use? Do I use this group standard error, which I'm going to calculate in a certain way, or do I use this group standard error? Or better yet, perhaps there's a way I can pool these two standard errors. Well, I just want to show you something. I'm not going to work this out now because I don't want to go back there. We're going to find another way to do this problem. I just want to point out to you that the difference here is that we're applying similar techniques to a categorical variable, diabetic or not diabetic, that we did to numerical variables when we're dealing with proportions, binomial proportions. However, we're going to need to generalize this a little bit because there's going to be times when our categorical variable has more than two categories. For instance, whether a person's exposure is none, medium, or high. When we're talking about someone's BMI, whether their BMI is too low, is in a good range, or is overweight, or is obese. Four categories, maybe 1, 2, 3, 4 for each one, representing each one of those categories. So how do I calculate this standard error? And I hope I have my piece of paper here. Let's see. See if I have it. Nope, that's not it. Well, yeah, I think I have. I can get it here on this sheet. I'm pretty sure it's going to come up here. Okay. Here's our various kinds of t-tests, I believe. So we can. Oh, I think it's up here. One sample, paired samples t-test. Nope, they don't have it here. Let me find my t-test. Nope. Paired samples. Nope. Just want to demonstrate to you we actually had this here at some point. Okay, let me try it this way. Let's see. There, I think it was called t-test variations, the document. Variations. Yeah, there it is. Let me open this up. Oh, sorry, I didn't open the PDF file. Okay, I think the last page. Here we go. Our standard error is going to be based on a pooled standard error. Here's the top part is the difference in the two proportions. The bottom part is our standard error. Okay, so it's just like x bar 1 minus x bar 2 divided by standard error gives you the number of t-scores apart, or if it's a very large sample, gives you the z-score of the difference. So our critical z-score is 1.96, right, for a 95% confidence. Alpha is equal is 0.05. So we're going to look to see if our z-score is bigger than that value. So how are we going to pool these? Well, they may be different sample sizes. Right? In this case, we got lucky to have the same sample size, but very frequently they're different sample sizes. So my pooled standard deviation is going to be equal to proportion 1 times sample size 1 plus proportion 2 times sample size 2 divided by sample size 1 divided by sample size 2. So you may notice that if you factor this out, then these two wind up canceling out anyway. So factoring out anyway. So, but if you have a large sample, if you have different sample sizes, they won't necessarily cancel out. So at any rate, our pooled standard deviation is going to wind up going in here. P times 1 minus P is our pooled standard deviation times 1 over our sample size plus 1 over our sample size 2. Right? So at any rate, notice there's no 1 or 2 on the bottom of this. So you can calculate a z-score. If your z-score comes out more than 1.96, you reject your null hypothesis that the true population proportion for group 1 is equal to the group population proportion for group 2. If your p-score is less than 1.96, You fail to reject your null hypothesis. So I don't want to beat this to death because we're kind of past this a bit, but we have a mechanism here that's very similar to the t-test that we use for comparing two proportions. We got another way that we're going to compare a couple of proportions that we're going to talk about tonight. Okay, and that's going to be odds ratio and relative risk. But now let's move on to that. And I'm really going to kind of freestyle on this. And I'm going to make up a new example. So let's say that we have a new population, right? And let's say that we have 1,000 people that we survey. And out of that 1,000 people, we had 200 people that are heavy smokers, and we have 800 people that are non-smokers or quit smoking. Okay, and out of those 200 people that were heavy smokers, we follow them for a long time, and we find that out of that, 50 people wind up getting chronic lung disease, one form or another chronic lung disease. 150 don't get chronic lung disease. Okay, out of the 800 people, out of this random sample of 1,000 people in this population that I took, out of those 800, maybe let's see, maybe 100 of them have chronic lung disease, and 700 of them do not have chronic lung disease. Well, this is a category. This is an example of two categorical variables. Okay, can anybody tell me what the two categorical variables are here? One represents an exposure, and the other represents an outcome. What's the exposure? No, the exposure, right? The outcome is whether or not they have lung disease, right? Right? Smoking, right? Okay, good, excellent, good. All right, good. I'm getting feedback on both ends here, here and online. Okay, so we have two categorical variables. How many values do we have for each? We have smoking, we have a yes and a no, and lung disease, we have a yes and a no. So in this case, we have two variables, each one of them with two possible outcomes. I'm going to organize that into a table. Remember when we did the diagnostic tests, we created a crosstab, a table which had columns and rows. Okay, and then the basic basis of the column and rows, the main part of the column and rows was the exposure in the rows and the outcome in the columns. So I'm going to call this column disease plus, this one disease minus, just like we did with our diagnostic test. And the exposure, I'm going to put here smoking plus, and smoking minus. They either did smoke or they didn't smoke. Okay, so I'm going to fill this out now. So how many people did we have that were smokers? Well, we had 200 people that were smokers. Out of the 200, so that's all the people in this row are smokers. Okay, so that's 200 people that are smokers. 50 of them were wound up with lung disease. Out of the and out of that same 200 people, 150 of them did not have lung disease. Well, how about the non-smokers? There were 800 non-smokers, and out of those 800 people, about 100 of them got lung disease. It wasn't like lung disease is limited to people that smoke, right? There are plenty of other people that get lung disease, and 700 people did not get lung disease out of these 800. Okay, so that's pretty interesting, right? So I have two groups of people here that came from a random sample of this entire population. Well, the total number of people that we sampled was 1,000. How many people out of that population of 1,000 actually got lung disease? Well, it's all the people that are in this column, right? 150. How many people didn't get lung disease? 850, right? So that's exactly right. Thank you, Sophia. That's 150 got lung disease, 850 did not get lung disease. What's the prevalence of lung disease in this population? 150 over 1,000, right? The prevalence in the population, everybody, right? There's the entire population, right? The prevalence in the entire population is 150 out of 1,000 people. So the prevalence in this population is 15% or 0.15. Okay. All right. So that's pretty interesting, right? Okay. So I'm gonna copy this all to the next page here. So I got a little bit fresh room here to work with. Okay. Smoking plus, smoking minus, disease, lung disease. I'll put LD negative. Okay, and this was 200. This was 800. This is 1,000. This is 50. This is 100. And this was 150. This was 700 and 200. And I made a mistake here somewhere. 700, 850. No, I didn't. Okay. All right, good. So the prevalence is equal to 15%. Okay, so now I'm going to make another box here. I'll make a second box here.
150, not 200.
What's that?
Lung disease total
Yes.
is 150, not 200.
Lung disease plus was 50. Lung disease was 200, right?
No, but look at the 200 next to the total of people with lung disease is 150, not 200. I mean, next to the 850.
You're pointing at that. I can't see where you're pointing.
Next to the 850.
Yeah.
It should be 150, not 200.
Oh, I'm sorry. You're right. 150. Okay. Yeah. There you go. Good. Thank you. Thank you. I hate looking back and seeing that later on and they can correct it. Thank you. Okay. So now I'm going to make another little box over here, right? And this little box is going to be, okay, so now nothing's going to change. 200 people in this population were smokers. 800 people were not smokers, right? So now I'm going to ask you, okay, and lung disease plus, and lung disease minus, and smokers plus, and smokers minus. Okay, now I'm going to ask you now, if the prevalence is 15% for the entire population, if there's no association between smoking and lung disease, I would expect smokers and non-smokers to get lung disease at the same rate. Both of them at the rate for the population, which is 15%, which we just figured out, right? So out of 200 people, how many people would I expect would get lung disease if 15% of them are going to get lung disease? Right? It's going to be 200 times 15%, which is, how about you guys online? Right? If the rate of lung disease is 15%, you got 200 people you randomly select, you'd expect 30 people to get lung disease, right? That leaves 170 people that didn't get lung disease. Okay? Well, how about if you have 800 people? Again, if you had a prevalence of 15%, how many people out of 800 would you expect to get lung disease? 120, is that right? I think you're right. Right? 15% of 800 is 80 plus half again is 120. Right? So 120. So how many people wouldn't get lung disease? Well, it's 120 from that. It's going to be 680. Right? And you'll notice that you get the same numbers down here, 150 and 850 and so on and so forth. Everything else stays the same. This is what we would have expected if there were no association between lung disease and smoking. Right? That's what we would expect. We're going to call this table our expected values. And we're going to call this table our observed values. Sure. Which part?
The second table represents the number of people.
The second table represents what we would have expected if there were no association between lung disease and smoking. We would have expected that smokers, the 200 smokers, would have gotten lung disease at the same rate, 15% would have gotten lung disease, as people that were non-smokers or as the general population, right? As a population in general, that 15% overall for the entire population. Okay, so this is interesting now. Let's take a look at this. One of the things I can see here is that in this box here, smokers that got lung disease, there's more people that got lung disease than I would have expected to get lung disease if there were no association. Instead of getting 30, I got 50, more than I would have expected. Well, how about for non-smokers? Well, for non-smokers, I see fewer got lung disease than I would have expected. If the entire population got it at the same rate. So I notice that there's a difference between these boxes. Okay, so I'm going to look at this. There are three ways that I am going to evaluate this. I'm going to rewrite this again because I want this to be a little bit clearer. I want this to stay clean and clear, as opposed to the way I usually write this junk. Okay, I'm going to go back here, and this was 50 and 150, and this was let's see, this was 100 and 700 as my observed values. Okay, and that's disease plus, disease minus, and this is smoking plus and smoking minus. And my expected values were, great, thank you, 30 and 170, 120 and 680. Okay, and these are my expected values. Disease plus, disease minus, smoking plus, and smoking minus. Okay, so now I want to see if there's an association between smoking and non-smoking. So I'm going to go up here. I'm going to write a null and alternative hypothesis. My null hypothesis, I'm not going to write this as a formula. I'm going to write this as a statement, is that there is no association between smoking and lung disease. And my alternative hypothesis is that there is an association between smoking and lung disease. That's my alternative hypothesis. So how am I going to prove this with this? Well, the problem is that these are my expected values. This is what I would expect if I could depend on every sample to give me exactly the proportion in the true population. This is what I would expect. Now, if I were to go and do this sample again, sample 1,000 people, right? Even if there was no association, I might not get exactly 30 and 120. I might get 31, 129, because just by sampling, there's a certain amount of variability that we expect in sampling. So just because there's a difference here doesn't mean that there's an association. However, if the difference is big, the bigger the difference is, right? The more likely that I can say that reject my whole hypothesis and accept my alternative hypothesis. So how am I going to figure out a way to determine whether or not that difference is big enough? Okay, well, the first way I'm going to do it is I'm going to invent, you and I tonight are going to invent a new statistic called ChiSquare. Okay, now, things happen, and sometimes somebody else discovers something before you. You go to the patent office and they tell you, nah, some guy in 1822 already developed that mousetrap, so we're going to reject your patent. So we're going to be very disappointed to find out somebody who's already done this, right? But we're going to make believe that we're going to invent a new statistic. Okay, so what is the statistic that's going to demonstrate whether or not the differences between this box, observed values, and the expected values is big enough to reject the null hypothesis? Well, I'm going to have to invent this statistic. So just like everything else, I'm going to take the difference between things, right, to see how big the difference really is. So I'm going to say my chi-square is going to be equal to, and I'm going to say it's the difference between the observed values and the expected values, right? So let's see, that's going to be 50 minus 20. And I'm going to do that for each one of these boxes. Observed minus expected plus observed. And I'm going to add up all the difference, minus expected plus observed minus expected. I'm going to do that for each one of these boxes. 50 minus 30 is 20. 100 minus 120 is minus 20. 150 minus 70 is plus 20. Just like before, we had a problem where we just add up the differences, they all cancel out, and we're not anywhere where we want to be. So rather than have those canceled out, I can either take absolute values or I can just square all of these. And that's what I'm going to do. And if I square all these values now they're all going to be positive and they'll all add up together. And the bigger the difference is between all of these, right? The bigger the difference between this box and this box, this box, this box, this box, and this box, this box, and this box. The bigger the difference is, the bigger is going to be the sum of this number here. Now, in order to bring this now, but the only problem is now these differences are magnified by the fact that I squared them. So in order to bring them back into the range of numbers that we're actually dealing with, I'm going to just say, well, we'll just take that and divide that by the expected value. 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 So now the numbers are more like what we started with, 20 and 40 and so on and so forth, right? So this is going to be my statistic. This is the way I'm going to calculate my statistic, my chi-square. Okay, and I'm actually going to do that. Chi-square is going to be equal to observed minus expected. Observed is 50 minus 30 is 20. Squared is 400 divided by my expected. 400 divided by 30. Plus, let's do the next one. Observed minus expected squared is going to be, I'm going to do the 100 here and the 120. Is minus 20 squared is 400. Again, 400. But this time over the expected value of 120. Plus, observed minus expected 150 minus 170 is 20 again. Squared is 400. Over my expected value, which is 170, plus 700 minus 680 is 20, squared is 400, divided by 680. Okay, so I'm going to work all of those out. Let me see what we get here. Okay, I'm taking so long here. This is less time that you're gonna have to be entertained by Levi. Hang on a second here. Why isn't this coming up? Yeah. Okay, I know what I got to do. I have to open this. I have to close it. Then I got to open it again, and it should come up. Yeah, there it is. Okay, good. So let's say 400 divided by 30 is equal to 13.33. Whoops. That's my eraser. 13. I'm just going to put 13. I'm just going to round it off the whole number for my purposes here. 40 divided by 120. 400 divided by 120 is 3.33. I'm just going to stick with whole numbers here. Plus 3, plus this looks like it's roughly going to be 2. This looks like it's going to be roughly 1.5, 1.1. Okay. 400 over 680. I'm sorry, is that 400 over 680? No, it's going to be 0.6. Okay, so if I add these all up together, my chi-square value is 18.6. Okay, pretty interesting, right? Now, how do I know if that number is big enough? Well, this is all based on chance. This is all based on if the prevalence is 30% or 15%. If there's a pooled prevalence that we can use for pooled standard error, well, I can figure out what these proportions represent. It turns out I can create a new distribution which takes a shape kind of like this. I'm sorry it's so small down here, which takes a shape kind of like this. Well, 0, 1, 2, 3, 4, 5, 6, and so on. The probability that if there's no association, the probability that you would get a big difference in chi-square is small, the bigger that difference becomes, the less likely that there's no association between that there is no association, that your null hypothesis is true. The bigger chi-square becomes, the less likely you'd be wrong if you reject your null hypothesis. In other words, the bigger the difference between your expected values and your observed values, the bigger this number chi-square is going to be, and the more likely you are to be justified in rejecting your null hypothesis. Well, what does this distribution look like? Well, it kind of looks like this. The idea that you would get exactly the same for your observed values as your expected values, that doesn't happen very often, right? When you take a big sample like this, if you took if if 20% of people that smoked got lung disease and you sample 1,000 people, you don't have to be awful lucky to get exactly 200 people, 200 smokers that had lung disease, right? So it's not real likely you're going to get zero. So we're going to start out pretty low for zero, but it is very likely that it's going to be close to zero. So the distribution might actually go up in the beginning, and then the likelihood that you would get a big value when there is no association it's going to go down, 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 down. And it's going to be asymptotic. It's never really actually going to equal zero, right? Well, if you look at this distribution, just like the normal distribution, the probability that if there's no association, your null hypothesis is true, that you would get such a big value for, say, a chi-square of 4, right, is the area under this part of the distribution. These are all the different outcomes that you could get if you did this over and over again. So as it happens, there is a value that we can call a critical value of chi-square. Okay. Now, I'm going to tell you for now that we could go to a table, a chi-square table. I think I gave you one. Okay, let me go to folder number. Okay, I think I gave you one here, chi-square table. Okay, and the chi-square table is just like when you worked with our t-table. The critical value, the size that chi has to be in order to have a probability of less than 5% chance of being wrong if you're rejecting the null hypothesis. Another way of looking at that, of having a less than 5% chance of having that extreme an outcome if the null hypothesis is true, 5%, is going to be in this column here. It's neatly shaded green for us, right? Well, the only problem is now we got to identify the number of degrees of freedom. Okay, now this I'm going to define for you. The degrees of freedom is equal to the number of rows minus 1 times the number of columns minus 1. So we got 2 rows, so that's 2 minus 1 is 1. We got 2 columns, that's 2 minus 1 is 1. 1 times 1 is 1. So for this particular application, the number of degrees of freedom is 1. So our critical value of chi-square is 3.841. Okay, that's our critical value. Now, did we exceed our critical value of chi-square? We're all the way out here, right? We're all the way out here. It's very unlikely we would get that big a difference if there was no association between these two, if the differences were just due to chance instead of an association between lung cancer and smoking. So in this case, we would reject our null hypothesis and accept our alternative hypothesis that there is an association between smoking and lung cancer. Okay, rows minus 1 times columns minus 1. Number of rows times 1 minus 1 times number of columns minus 1. So that's chi-square. Now, when we use SPSS, SPSS will not only calculate the value of chi-square, but it'll also give us a p-value, right? And that p-value, we want that p-value to be less than alpha, less than our acceptable level. We want that to be less than our acceptable level of error, which is 5%. So it'll actually give you a p-value. In this case, the p-value might be 0.001 or something like that. It'd be a very small number. It'd be way less than alpha because our chi-square value is way more than our critical value of chi-square, which was 3.84. Okay, all it had to be is 3.84 or bigger, in order for us to reject the null hypothesis. Okay, so that's one way we could look at this chart. That's one way we could evaluate whether we can reject the null hypothesis. Is this idea of chi-square. I'm going to redraw this one more time to show you another way we could look at this. Okay, and actually I'm not going to bother with the second table. This was 50 and 150, and this was 100 and 700. I'm right, correct? Okay, disease plus, disease minus. Yeah, okay, and this is smoking plus and smoking minus. Another way that I can look at this is say to myself, this is 200 people that were smokers, 800 people that were non-smokers. Another way I can look at this and say to myself is, what's the rate or the risk of getting lung disease if you're a smoker? Well, the risk is equal to, for smokers, the risk for smokers is equal to 50 out of 200. And that's equal to 25%, 0.25. Right? So if you're a smoker, your risk of lung disease is 25%. Well, what about your risk if you're a non-smoker? Your risk of getting lung cancer is 100 out of 800 people. And that's equal to 1/8 is 0.125. Okay? Okay, I know that because because if you ever cut a piece of wood, 1/8 of an inch is 0.125. Right? So at any rate, 0.125 is the probability, the risk that you're at for lung cancer if you're a non-smoker. Well, look at this. The risk for a smoker is twice as much as a risk for a non-smoker, right? Okay, well, let me do something here. Let me say to myself, why don't I take the risk for smokers, divide that by the risk for non-smokers, and see what that ratio is. So it's 0.25 over 0.125. 0.125 goes into that twice. That's 2. You're twice as likely to develop lung cancer if you're a smoker than if you're a non-smoker, according to our observed values. I'm going to give that a special name. I'm going to call that the relative risk, or risk ratio. A lot of people call it risk ratio instead. That's simple, right? Now, let me ask you something. Our null hypothesis is that there's no association. Our alternative hypothesis, there is an association. Okay? If there's no association, what would you expect your relative risk to be equal to? You would expect the risk for smokers to be the same as the risk for non-smokers. You'd expect it to be equal to 1, right? Because you'd expect the top to be the same as the bottom. Wouldn't expect any difference between smokers and non-smokers. Excellent. Good. Very good. So now our next problem is, well, gee, 2, is that big enough for me to say, is that a big enough difference from 1 for me to reject the null hypothesis based on the relative risk and accept the alternative hypothesis? Well, the only way I'll know that is if I calculate a confidence interval for this outcome. In other words, it's nice, it's 2, but at the confidence interval, because the sample is small, the confidence interval is 0.9 to 3.1. I can't reject my null hypothesis because it could be 1. But if my confidence interval is 1.5 to 2.5, well, then we're 95% sure it's not 1. So I can reject my null hypothesis. So I actually have to calculate a confidence interval, not just my relative risk. We're not going to do that by hand. We're going to take advantage of SPSS. So now I'm going to give you another way of looking at this now. Okay, so I'm going to take this again. Okay, I'm going to take this one more time. Notice how we're using these same numbers and we're finding many different ways to approach this. Okay, and 100. Okay, now tell the truth. How many of you guys play the ponies? Anybody here, in the old days, used to go to OTB or maybe show up at the track? Any railbirds out there? Refer to people that like spend too much time at the track as a railbird. Any railbirds out there? Oh, okay, April. Good. I knew we'd get at least one. Okay. So now you railbirds know that when you go to the track and you look at the tote board where they have the odds, right? You might see a horse is 3-1. Well, that doesn't mean the horse is three times as likely to lose the race or win the race, right? Actually, 3-1 is 3-1 is odds. 10-1 is worse than 3-1, right? It doesn't mean that the horse is three times as likely to win or lose. What it means is that if the race were run four times, you'd expect that horse to lose three times and win once, right? Kind of a funky way of looking at this, right? You would have thought, well, gee, why don't we just call it 1/3, instead of that? And a 10-1 would be if they raced 11 times, that we'd expect that horse to lose 10 times and win once. Why do they do it like that? Because it's easier to calculate the payoffs. When you calculate the payoffs, you can say, well, $2, like $2 will pay off 10 so much, right? Instead, that way. So it's easier to calculate the payoffs if you use odds instead of risk on the tote board. So we're going to look at this in terms of odds as well. Okay. So instead of saying, well, if we were going to look at risk, we would have said 50 out of 200. If we were going to look at a risk for non-smokers, right? This is non-smokers, this is smokers. If we were looking at risk for non-smokers, we said 100 out of 800. That's what we did up there. And then said one over the other is the relative risk. Now, for odds, we're going to look at it differently. For odds, we're going to say the likelihood of having lung disease versus the likelihood of not having lung disease within that group. So the odds for smokers is going to be equal to 50 over 150, or it's going to be equal to 1 over 3 or 0.33. A little bit different number than we got up there at 0.25, isn't it? Right? But it's calculated a little bit differently. Okay, lots of us. Okay, good. So what about the odds for non-smokers? The odds for non-smokers, again, if we were risk, we were looking at, we'd say 100 over 800 would be 0.125 or 12.5%. But the odds are 100 out of 700. Okay, if you had 800 people, 100 would have lung disease, 700 would not have lung disease. So it's 100 over 700. And those odds are, let me calculate that. Okay. Don't use that much in a lumber yard, so I got to use my calculator. 1 over 7. Okay, same ratio, right? It's going to be 14%, let's call it. It's going to be equal to 0.14. Right? So my odds, notice that I'm getting the same kind of result. My odds for smokers getting cancer are going to be bigger than my odds for non-smokers, right? So it's not as if we're getting a different result. We're going to wind up with a different number though. Now, just like I did before, I'm going to calculate an odds ratio, right? So odds ratio is going to be equal to the odds for smokers, exposed people, over the odds for people that were not exposed. So the odds of getting lung disease for smokers is 0.33 over 0.14. So our odds ratio, OR, our odds ratio is going to be equal to, clear, 0.33 divided by 0.14. 2.36. Okay. So our odds ratio is going to be equal to 2.36. Okay. So we got a different number than we do for relative risk. Relative risk comes out 2. Odds ratio comes out 2.36. In all cases, you will always get, if the relative risk indicates a elevated risk for people that are exposed, the odds ratio will indicate an elevated risk, but they may not be exactly the same number. Okay, so which one is more popular when you do studies and you publish papers? As it happens, more often than not, you'll see people use odds ratio. There's a lot of reasons for that. I don't want to beat this to death. Personally, I don't know about you guys, but I find relative risk to be much more intuitive in terms of wrapping my head around whether or not how much the risk is increased from that exposure. But odds ratio in most papers is more popular. Well, let me ask you something. I'm going to calculate a confidence interval for this odds ratio now. And what does that confidence interval, what odds ratio does that confidence interval not have to exclude, not be within that odds ratio? What number would suggest that there's no association between smoking and cancer? What do I not want that to be in that? Not zero, right? Because it's a fraction, never going to be zero. It's going to be one. Because if it were one, that would indicate the odds for non-smokers is the odds for smokers is the same as odds for non-smokers. These two percentages, these two odds are the same, so that would indicate a one would indicate there's no association. Now the question is whether or not there's a big enough difference than 2.36, and that involves the sample size and so on, and that odds ratio of one. And for that, we're going to depend on SPSS to actually do these calculations so they don't get too cumbersome for us. Now, I might ask you, say, on the test that we give you, I might ask you to do an actual calculation involving the chi-square, because that's pretty simple calculation, right? You saw how we did that. Oh, I don't know where the page went, but you guys saw how we did that. Okay, but for odds ratio and relative risk, if I'm going to ask you to decide whether or not to reject the null hypothesis, I'll either ask you for SPSS to use SPSS or R or whatever software program that you want to use, or I'll provide you with an output chart like I did on the exam for analysis of variance, so you can make a determination about it. So that's it. That's what this stuff is all about. These are the three things we learned tonight. We learned about a new way to deal with a new set of statistical tools that allow us now to deal with categorical variable. Yes or no, exposed, not exposed, not numerical variable. Blood sugar levels of 0.97 versus blood sugar levels of 0.75. Not numerical variables, but categories. Yes, you get disease. No, you're not. Don't have disease. Yes, you're exposed. No, you're not exposed. Now, just one other thing is that when we're dealing with this, you can also have situations where we can have more than one row and one outcome. So, for instance, you could say, let's say left-handed people and right-handed people. How likely are they to have diabetes? How likely are they to be redheaded? How many of them are redheaded? How many, and so on and so on. You could have a lot of categories, you could have multiple exposures, like BMI, high, medium, and low. You could have tables that are 3 by 3, so on and so forth, 4 by 3, and so on and so forth. We can still calculate chi-square for those. A little bit when we deal with odds ratio and relative risk, we're exclusively dealing with 2 by 2 tables. But chi-square, we can work with chi-square tables that are multiple rows and columns, and to determine whether there's an association between an exposure and a whole bunch of different outcomes. But when we do that, when we go to our table, we're going to use a different number of degrees of freedom. So, for instance, if we had 3 rows and 4 columns, right? That would be 3 minus 1 is 2, 4 minus 1 is 3, 3 times 2 is 6 degrees of freedom. And for 6 degrees of freedom, we would have to have a chi-square value when we add up all those different cells of 12.59 or larger in order to reject the null hypothesis. Okay, so let's take a break from this. Take 5. Have a bud. Listen to Levi's lecture for. Try and scrub through it. I really kill a lot of time here on this introduction, but I really do want to get on some examples. Try and scrub through it. I'll give you about maybe, let's see, come back at about 7:40, 7:40. No, that's, yeah, come back at 7:40. Now let's make it 7:30. Come back at 7:30, and you'll all have a chance. You will have a chance later on to hit the lecture again, in more detail. But come back at 7:30, and we'll go through some examples on this. Okay, so I'll see you guys shortly. Okay, any questions before you go away? Okay, and okay, good. You can reserve the question. Like if none right now, you can reserve the questions for later on. See you in a little while. Bye.